So the topic is SweRV Cores roadmap, and the agenda for today, just briefly introduce Western Digital RISC-V history, then explain the SweRV Cores roadmap, and then I have the honor to have Robert Golla, our chief architect, sort of explain the key features of the SweRV, new generation of SweRV Cores. And if time allows, towards the end, we'll talk a little bit about how this fits into our flash controllers. So our history started about 5 years ago. We were one of the earliest members of the RISC-V and work on the RISC-V becoming a standards organization for RISC-V instruction set architecture. A couple of years ago, we announced, our CTO, Martin Fink, announced plans to transition our cores to RISC-V cores. This presentation today explains a little bit of details about how we're doing about that. This is the roadmap of many open source RISC-V cores. I don't have all of them here. SweRV EH2, when originally came in last year, when we announced it, filled an important gap, which is a sort of high-end performance embedded core. So not quite like out-of-order performance you need for applications processor, but core that is faster than your traditional single-issue classical pipelines. And today we are explaining our second generation of cores, SweRV EH2, which is a performance upgrade to SweRV EH1, and an ultra-small, wickedly fast SweRV EL2 core. And in terms of the features, SweRV second generation cores is targeting 16 nanometer technology. The EH2 core will be 0.07 millimeters square in 16 nanometers. Obviously, good deal of improvement is because of transitioning from 28 to 16, but it's basically a core that's very similar in size to SweRV EH1, and introduces a capability to run 2 threads, this multi-threaded core. So that's actually very cool, and at least in the world of verified open source RISC-V cores, this is the first one. And then SweRV EL2 is super small, super fast cores that's targeting sequencers, any kind of FSM you need to implement your SoC. And the SweRV EH1, we talked about it to great level of details last year. Just to kind of recap before I let Robert explain EH2 and EL2, EH1 was a 9-stage pipeline, dual issue, superscalar therefore. And the 2 key features on this core were the fact that it was a dual issue and the fact that it had 4 execution units, which together combined enabled this core to have about 50 to 60% better performance than classical pipelines, and got it to run core mark nearly at 5 core marks per megahertz. I think literally it's 4.96 or something like that. So, Robert, you have the honors.
Thank you. So just to add a little more to EH1, we announced that at last year's summit. We open sourced it in January of this year. And on that slide, there's a link to Chips Alliance, and you can download it from the GitHub link there. So this year we've been working on some second generation cores, and there's 2 of these. The first is EL2. And not all of our customers need the performance of a dual issue in order core like EH1. A lot of our customers, their primary focus is to have minimum area and low power, low cost, and reasonably good performance. And for that reason, we decided to make a sort of smaller core called EL2. It's second generation, leverages a lot from EH1. It's RV, 32 IMC, just like EH1 is. We added bit manip instructions. We added the ZBB, ZBS extensions. It's a 4-stage pipe from fetch to commit. It has a non-blocking architecture. I'm going to talk about that a little bit more on the next slide. And the main focus of EL2 was to achieve a 1 IPC on all the workloads that you run that run from local memories. So if you're running from the iCache or the ICSIM or the DCCM, and you're running just from there, we try to run at 1 IPC. And so that kind of guided all the design decisions that we made. EH1 has a 1 cycle taken branch penalty, but that we couldn't afford to have that on EL2 if we wanted to run at 1, so we have a 0 cycle branch target buffer. We don't have 4-cycle, 7-cycle mispredicts like we do on EH1. We have a 1-cycle branch mispredict. And then even that's not quite good enough if you want to run at 1 IPC, because branch mispredicts, if you don't have a branch predictor, you have a 1-cycle taken branch mispredict penalty. So branches conservatively might be 20%, taken branches 50%. You're going to have like a 0.1 CPI loss. So we put a branch predictor in that you can build in, and that reduces that loss to 1 to 2%. Our load to use latency is 1 cycle, and you put all that together, and you end up, almost all applications that run from our local memories run very close. You run in the 0.9s, and you'll see some of that later. Another thing we did on our 2nd generation cores is we added some fast interrupt support. So on EH1, when you have an external interrupt, it goes to our PIC controller, and it prioritizes the interrupts, presents it to the core. We go to the standard RISC-V handler, we look up the claim ID, and we jump to the corresponding interrupt service routine. With fast interrupt support, the hardware does the first part of that handler. We figure out the claim ID ourselves, we look up where to go, and we jump directly to the corresponding ISR. So that saves us all the code in the first handler, it saves us the flush, and the net is we have faster interrupt latency. We also have a little enhanced DMA support. We're fully pipelined on the DMA accesses that come off the slave, on the slave port on the bus. EL2 has a dry stone of 2, and I agree with Patterson, this benchmark needs to be retired. It has a core mark per megahertz of 3.6. The target frequency was 600 megahertz, and that's in TSMC 16 nanometer, worst case corner. And the area goal was 0.025, and currently we're at 0.023 on the design. Okay, the next core is EH2. And as we look towards our future products and what their performance needs were, it became pretty clear to us that we needed to improve the overall core performance. Our current products are already multi-core. So one of the options we have is we could have just put down more cores, but we analyzed the current workloads that we have internally, and it turns out the core pipeline is not heavily utilized. And because of that, threading becomes attractive. And the nice thing about threading, we talk about these core logic and the pipelines, but the core itself is made up of the core logic and the memories. And the core logic itself on our typical use cases is probably 10 to 20% of the total core. The rest is the memories. So when you add threading to this core, the total area growth for the overall core is in the 5 to 10% range, as opposed to if you plop down a whole nother core, it's 100% growth. So it's a lot more efficient. And that was mainly the thrust behind why we added threading. And you can build this core with 1 thread, or you can build it with 2 threads. If you build it with 2 threads, then for those applications that have a single thread IPC of less than 1, you're typically going to see a gain between 1.6 and 2x. That's what we're seeing. We have the same fast interrupt support, same DMA support. We get a dry stone score of 2.9, and we get a core mark megahertz 4.9 for 1 thread, and that's essentially the same as EH1. But with 2 threads, we get 6.3, and actually the latest design is getting 6.5 because we made some more improvements. Target frequency is 1.2 gigahertz, and that's in TSMC 16 nanometer, worst case corner. And I left off one thing, the non-blocking microarchitecture. EH1, we don't know that we're going out to the system bus until we get to the DC3 pipe stage. And it's possible to have dependents that are in the pipe, so we freeze the pipe for EH1, and that's fine because it's a single-threaded machine. In a multi-thread machine, you don't want that. You never want your threads to block the other thread. So what we do instead is we basically figured out a way to calculate that in the DC1 pipe stage, 2 stages up. And then if we have a dependent, we'll cancel it and we'll replay it later, and we free up the pipe for the other thread. So that's one thing we did. The other thing we did on both of these cores is we made all the divides non-blocking. So when one thread is doing a divide, the other thread has full access to the machine. Okay, what do you do to thread a pipeline? To thread a pipeline, you need to, first thing is you add the second thread, you need to double the architectural state. So in practice, that means all the integer registers and all the CSRs. The second thing you have to do, for some of your microarchitectural state, you have to double that. And then where your pipe has stalls, you need to put in an arbiter generally. So in our machine, we start at the top, we duplicate the fetch address register and the logic associated with it, and then we use a least recently fetched algorithm when we have two ready threads to pick one of them to run down the machine. We do a similar thing right before the aligner. We have two fetch buffers. Each has 4 entries each. We made a small change on this core. We do 8 bytes. We fetch 8 bytes. It's more efficient than what we were doing on EH1 because we fetch 8 bytes all the way across the cache line until the very end. And we use a least recent, well, we used to have an arbiter here, but we took it out. The aligner logic is not that big, so we duplicated the align logic, so we have 1 aligner per fetch buffer, and then we align directly into the corresponding instruction buffer. So on EH2 and multi-thread mode, both threads are simultaneously aligning instructions and feeding down into the instruction buffer. At decode, that was the last, so we don't have an arbiter there. We have an arbiter at decode between the instruction buffers. Once again, you have to duplicate that for each thread. And there's 4 instruction buffers per thread. And so we have sort of a least recently decoded bit that we use. We call it a favor bit. We favor one thread or the other. And the reason we have this favor bit is because we only have 1 load store pipe. We only have 1 multiply pipe, 1 divide pipe. And in addition, although these pipes are almost fully symmetric, they're not completely fully symmetric. On EH1, the CSRs are only executed on the I0 pipe. Some of the instructions that have pre-sync and post-sync are executed on the I0 pipe. And so for these reasons, we needed a way to get fair access to these things that can only run 1 operation. So when you have 2 threads, we use the favor bit to schedule the favorite thread onto the I0 pipe. And then the other thread, if it's present, will go onto the I1 pipe. So what this leads to in practice is that the threads sort of oscillate on the I0 pipe and they're running in threaded mode. Decode is primarily the one that schedules everything in an optimal fashion down the pipe for threaded performance. So like if a load is missing out on the system bus, that thread is removed from arbitration and the other thread will get full access to the pipe. If a thread is running a divide operation, that thread will be removed from arbitration, the other thread will get full access to the pipe. If we have 2 loads and one of them is going to be favored, then the other load won't participate in arbitration, and the favored thread will send 2 instructions down the pipe, the load plus the other instruction behind it. Same thing for multiplies. If any thread has a pre-sync or post-sync, it won't participate in arbitration. And we did this to everywhere we could. If a thread is stalled, it doesn't participate, and we give everything to the other thread for execution. Okay, so a quick example. This is the H2 pipeline, and at the very top we have 2 threads. Thread 0 is green, thread 1 is red, and the top of the pipe is vertically threaded. You can only have 1 thread or the other in the fetch 1 and fetch 2 pipe stages. So using the least recently fetch, we would pick 1 and send down the pipe. Once we get down to the aligner, you can have both threads present because they can both align simultaneously. At decode, you can have both threads present. And then as you can see looking down the pipe, you can see how these typically oscillate when both threads are ready. You'll have red, green on the I0 pipe. And the last thing, so from a line down, we call that SMT, simultaneous multi-threading, because you can have both threads present per pipe stage. Commit can commit up to 2 different threads per cycle. And this guarantees that even if both threads are executing serial code, that you can still get an IPC of 2 in multi-threaded mode. So an example here, this is a multi-threaded example of merge sort, one of the C programs we have that we use for performance analysis. This is measured at the commit stage, and on the left-hand side is a cycle that the instruction committed, and I have a little trouble seeing it. But the blue is thread 0, and the red is thread 1. So if you were running in single thread mode, you would only see the blue. The red would just be stall cycles. And when we run the 2 of them together, the red sort of, in this example, it interleaves nicely between the 2. So in single thread, the blue only, you have a 0.79 IPC. When you run them both together in the interleaving, you get an IPC of 1.5. And the net multi-thread gain is about 1.9x. And this is all running from the system bus. So it's about 11 cycle load to use. This is what we typically see when we're running from the system bus. So performance of EL2 and EH2. So the SweRV EL2 performance for applications that hit to the iCache ICCM and the DCCM, the IPC is going to be close to 1. On CoreMark with our small BTB, it is 0.95 IPC. If we put in a larger BTB that we have, our largest option, it goes up to 0.97 IPC. It can never be greater than 1 because it's a single issue machine. Drystone is 0.98 with a small BTB. With a larger BTB, it goes up to 0.99. So I feel that did pretty good on the microarchitecture because that's what we designed it for. As for EH2 performance, you can expect the single thread performance to be essentially the same as EH1. And the multi-thread performance, it varies quite a bit depending on what you're running. So to get an idea of this, we kind of did a statistical way of approaching this. We wrote a bunch of C programs ourselves. We got a lot of C programs from our firmware group, and we threw CoreMark into it, and we generated 120 workload variations where we ran all these programs. I think there was about 16 in all. We ran them homogeneously, ran them the same on both threads, and we ran them from the DCCM only. We ran them from the system bus at 10, 15, and 20 cycles. And then we also did that, we picked a subset of that, and we ran all combinations heterogeneously. So we did all that, came up with 120 variations. And on the x-axis, we plotted the ST, the single thread IPC, and on the y-axis, we plotted the multi-thread IPC. So you can see below 1, we have sort of that dotted green line. That would be the ideal line to be on. You would be 2x. When you add the second thread, you'd be twice as good as single thread. And below 0.5, it's very close to that line, and the average is 1.95. Between 0.5 and 1. On this slide, it says 1.83. The latest design is actually 1.86. And then once you get to 1, you're no longer guaranteed. You're not going to double because this is only a 2-issue machine. So you're capped at 2. So between 1 and 1.5, the average gain we see is 1.36. And between 1.5 and 2, the average gain we see is 1.13. And that's pretty much it.
Cool. Thank you, Robert. Okay. So very quickly, what is a typical application? We talked a little bit about this last year. If you look at the sort of a generic flash controller architecture, you'll see one processor core at the front end handling a host attachment interface, and you'll see a secondary set of cores handling flash controller sequencers that actually talk to the NAND flash devices. In addition to that, you have other opportunities for RISC-V cores, like a power management core, root of trust core, etc. So we started with the first project with the data processor core, and now we are in new projects moving to sort of encapsulate other opportunities. So my prediction is that the main CPU or that host controller interface, controller core, will be our next target for RISC-V. Really kind of gunning for a RISC-V homogeneous SoC. And that's our conclusion chart. We continue our strong commitment to RISC-V. We find a super strong sort of magnetic force whenever we have a new project inside Western Digital. RISC-V is always kind of the best running option due to the flexibility. And we are releasing and open sourcing our second generation of SweRV cores, and we are doing that through Chips Alliance. And for our first generation of cores, we have also enabled CodaSIP as a commercial support vendor. So we are committing that the source code remains open, but there is a vendor who is actually professionally set up to provide a processor support package and design verification services around SweRV. So thank you very much, and we have a time maybe for one question. So. All right, go ahead.
Why didn't this course choose Chisel as the implementation language?
Why did what? Sorry.
Why didn't choose Chisel as the implementation language?
Oh, that's actually a great question. So actually, Chisel workgroup is one of the workgroups, very active workgroups in Chips Alliance. And it's I think it's a great tool for SoC level integration, but there was no reason to insist on sort of coding the RTL for sort of real-time embedded core in high-level languages, going straight to RTL, meaning to Verilog, is sort of the optimal thing. You can still encapsulate it with Chisel and build your SoC or even larger systems with Chisel, and that's where Chisel really shines. I think for a core IP, it wasn't necessary, at least not for my team in Western Digital.
So I would say quickly that the language you use to code your core is not usually the gating factor. I mean, we're not building hundreds and hundreds of cores. We're trying to build the best core we can. So using system Verilog doesn't hold us back in any way, vis-a-vis Chisel. Plus Chisel has, it's not an industry standard at some level yet. So for commercial support, that may be changing, but it doesn't hold us back in doing this core. That wasn't this core was actually designed in about 3 to 4 months. The multi-thread.
That's pretty quick design. The question is, when you're replacing the ARM cores or some other proprietary instruction set, what is the challenge? How do you go around, enabling your ecosystem, your stack, when you're replacing a processor with the different instructions?
Great question. So in reality, we're not really replacing any existing cores. There's plenty of legacy projects. And as they transition to the company, it doesn't really make sense to replace anything if you have firmware. My experience is really with new projects, right? But still, it's still a valid question. What is the strategy? How do you really make this work and accelerate it? Our strategy for this was exactly open sourcing. We felt that open sourcing high quality verified RISC-V cores will help others adopt it. And we also open sourced our RISC-V firmware toolchain work that we have been doing, which is really a set of low-level tools that enable firmware programmers to use these cores. So we really share all these with, within the RISC-V communities, and that's how we are sort of accelerating ecosystem. And we had actually great success in this area as we reported in other conferences. We had the presentations on GNU Cauldron where we actually reported on our work on the toolchain.
Thank you.
And I think we had yesterday's presentation by Nidal Faur here as well on the same topic.
Hi, I think I noticed kind of a blank box on the roadmap slide. Do you want to comment
Finally,
on that?
somebody, after 14 months, having published this on 2 websites and a magazine, somebody has asked, well, you can guess from the positioning, You can guess from the y-axis what it could be. Yeah. All right, I think we're over. Feel free to stop me in the hallway and ask me any questions related to anything. All right, thank you.
Thank you.